welcome you to my third lecture on network functions. In today's lecture, we shall see the concepts of poles and zeros and what are their significance, and also solve some tutorials based on these concepts. So let us see first what are these poles and what are these zeros. So let us consider a function h of s, which is Laplace transform of output by Laplace transform of input. So here output polynomial let us assume to be p of s, and input polynomial let us assume to be q of s. So here this expression I can write as a0 s power m plus a1 s power m minus 1 plus a2 s power m minus 2 plus so on to a power am. Similarly, q of s I can write as b0 s power n plus b1 s power n minus 1 plus so on till bn. Here, as you can see, we have assumed the degree of numerator to be m, and we have assumed the degree of denominator polynomial to be n. So in other words, I can say that the numerator has m factors and the denominator has n factors. So this expression h of s I can rewrite or write in factorizing form, that is some constant k into s minus z1 into s minus z2 so on till s minus zm. Similarly, the denominator can be written as s minus p1 into s minus p2 so on till s minus pn, where here z1, z2, z2 on zm are the roots of the numerator polynomial p of s, and p1, p2 so on till pn are the roots of the denominator polynomial q of s, and k is a scale factor or gain factor. So from this expression we can see the numerator becomes 0 when s is equal to z1, z2 so on till zm. Similarly, the denominator of this expression becomes 0 when s value is equal to p1, p2, p or till pn. So the values of s for which the given system becomes infinite or the denominator of the function becomes 0 are called poles. So in this expression, this function becomes infinite when s value is equal to p1, p2, p3 so on till pn. So these p1, p2, p3 so on till pn are called poles. So these poles can be real or and non-repeated. This can be complex poles and this can also be repeated poles. So we'll see later what are the different types of poles that can exist for a given polynomial. Similarly, if this function has to become 0, then s value should be equal to z1, z2 so on till zm. So this the values of s for which the system function becomes 0 are called zeros of the system. Here z1, z2 so on till zm are the zeros of the given function. Similarly, as in poles, here zeros also can be simple poles or repeated zeros, simple zeros or complex zeros. So as we can see, the poles are the values of s which makes the given function to be infinite. Similarly, the values of s for which the given function becomes 0 are called zeros. So let us see what are the significance of these poles and zeros. So before that, let us try to understand that by means of a simple example. If our h of s is given as 10 into s plus 4 by s into s square plus 2s plus 2, the numerator becomes 0 when s value becomes minus 4. The denominator value becomes 0 when s is equal to 0, or if I find the roots of this expression, it will give me minus 1 plus or minus j. So in this case, we have 3 poles and 1 zeros. So s is equal to minus 4 is nothing but 0, and S is equal to 0, minus 1 plus or minus j are the three poles of this expression, where 10 is the scaling factor. So in this way we can find the poles and zeros of a given function. So the DC gain. So let us consider h of s to be 20 into s plus 2 into s square plus 2s plus 5. So then let us find the value of h of s when s is equal to 0. So if s is equal to 0, this value becomes 20 into s by 5, which is equal to 8. So this is called the DC gain of the system. So I can define DC gain of the system is nothing but a complex frequency function. So the value of h of s at 0 function, that is at s is equal to 0, the value of h of s is called DC gain of the given system. Pole 0 plot. So if I take a S plane, so here you can see this is your imaginary axis, which is j omega axis, and this is your real axis, which is denoted by sigma. So in this called S plane. So in this S plane we have to indicate poles and zeros. Generally poles are indicated by cross symbol, whereas zeros are indicated by zero symbol. So let us see how to plot a pole zeros in a pole 0 plane or S plane. Let us take an example, 20 into s plus 1 into s plus 5 by s into s plus 7 into s square plus 2s plus 2. So here zeros are nothing but s is equal to minus 1 and s is equal to minus 5. So this is your S plane. So as we know, zeros are represented by 0. So at minus 1 I have 1 0, and at minus 5 I have 1 0. Poles are nothing but 0, minus 7. If I take the roots of this equation, I will get minus 1 plus or minus j. So I'll have, so poles are represented by cross. So at 0 I have a 1 pole, at minus 7 I have 1 pole, and next minus 1 plus or minus j. So minus 1 plus j is 1 pole, minus 1 minus j is another pole. So this is how we plot a pole zeros in a S plane. So next is the significance of poles and zeros. So let us see what is the behavior of the system in time domain from pole 0 plot. So before that we should understand that from pole 0 plot we can easily identify whether the given network is stable or not. So depending upon the location of poles, especially poles. So the location of poles in the network will help us to find the time domain behavior of the system, which in turn will also give me the stability criteria of that system. So let us consider different cases and learn the time domain behavior of the given function. First case, let us assume the pole is at 0, origin. So the pole is at origin, the function will be in the form of some constant k by s. So this indicates that there is a pole at origin. So if I apply inverse Laplace, it will give me some constant value. So that means if I have a pole at origin, so its time domain behavior will be nothing but a constant value. Hence we can conclude that if there is a single pole at origin, the time domain response is nothing but a steady state value or a DC value. The second case, if the pole is located in left hand side of the S plane. So if the pole is on left hand side, that is represented by f of s is equal to 1 by s plus 2, because in this s value is nothing but minus 2. So this function indicates the pole is at left hand side of the S plane. So upon inverse Laplace transform, which will give me e power minus 2t. So e power minus 2t indicates it is exponentially decreasing. So as you can see, if I have a pole on left hand side of the S-plane, this indicates that the function is exponentially decaying function. So therefore we can conclude that if I have a single pole on negative real axis, then time domain response will be exponentially decaying function. The third case, if the pole is on right hand side, so before going to right hand side, so here we have considered only one function. Suppose that if I have two functions here, f1 of s I will take 1 by s plus 2, and f2 of s I will consider 1 by s plus 5. So here upon inverse Laplace, which will give me f1 of t is e power minus 2t and f2 of t is e power minus 5t. So here as you can see, I have a pole at minus 2 and I have a pole at minus 5. So in both the cases the function will be exponentially decaying, but here we can observe that the farther I go from origin, the decaying expression, as you can see, is at faster rate. So I can conclude that as the pole moves away from origin, the function in time domain will decay at a faster rate. So you can see the decay is faster when compared to the previous case. So therefore, in other words, I can also say as the pole moves towards the origin, the time domain decay will be at a slower rate. So next, the third case is when the pole is at right hand side. So that is represented by 1 by s minus 2. So here s value will be nothing but plus 2. So here the pole is located on right hand side of the s-plane. So on inverse Laplace, which will give me e power 2t. So the exponential term is positive. It indicates that the response is exponentially increasing. So here we can conclude that if a single pole is located on right hand side of the s-plane, in time domain its value will be exponentially increasing. So this value will go on increasing till it will lead to instability. So therefore in this case there is no control over the exponential function. So from this we can conclude that if the poles are located on right hand of the s-plane, the system is unstable. So for a system to be stable, all poles and zeros must and should lie on left hand side of the s-plane. So similarly, the fourth case, if we have a pair of complex conjugate poles which lie on imaginary axis only. So let us consider the expression f of s is equal to some constant a into omega by s square plus omega square. So if I find the poles, which will give me s is equal to plus or minus j omega. So upon inverse Laplace, which will give me a into sine omega t. So that indicates that in time domain it is of sinusoidal function. So from this we can conclude that if a pair of complex conjugate are present on imaginary axis in time domain, its response will be in sinusoidal form. So here as you can see, if there are complex poles, conjugate poles on imaginary axis in time domain, it will be of oscillatory response or sinusoidal response. Similarly, if I have number of complex conjugate poles on imaginary axis, suppose in this case 10, 100, 1000. So as you can see, as we go further, the omega value increases. So since frequency is directly proportional to omega, so we can say that the farther the conjugate poles move from origin, the value of frequency also increases. Since the higher the value of frequency as the poles move away from origin on imaginary axis. Similarly, with the pair of poles move towards origin, the frequency will reduce, since omega and F are both directly proportional. The fifth case, when the pair of conjugate poles have a negative real part. That is, if the expression is in the form some constant A into omega by S plus alpha square plus omega square. So here complex conjugate has some real part, because if I plot this S plane, S value will be nothing but minus alpha plus or minus j omega. So here S value, the complex conjugate has some negative real part. So this upon inverse Laplace will give me A into e power minus alpha t into sine omega t. So here you can see this consists of both exponentially decaying function as well as a sinusoidal function. So from this we can observe that if the complex conjugate have negative real parts, it will produce damped oscillations as shown in the figure. So suppose I have two functions of this type, that is minus alpha plus or minus j omega 1 and minus alpha 2 plus or minus j omega 2. So here in this case, if I have more than one complex conjugate having negative real part, then here also we can observe that in first case you can see the frequency is small and the rate of delay is very small. And in the second case, you can see the rate of decay is very fast, frequency is very large. So from this we can conclude that as we go farther from the origin, the decay becomes fast and the frequency becomes large. Sixth case, if the complex conjugate poles have positive real part. So if the complex conjugate has positive real part, it also has both exponential term as well as sinusoidal term. So since this is exponential term with positive value, it will produce a sinusoidal waveform with increasing amplitude, since there is no control over this. So since it is having a positive real part, so here also in time domain the response is tending to infinity, which is making the system to be unstable. The next case, if I have two poles at origin, that is 1 by s square, indicates that I have two poles at origin. So which will give me in time domain to be t into u of t. So in such cases also we can say that the system is unstable. In time domain this value is linearly increasing and this extends to infinity. So even this system will tend to go into unstable when two poles are existing at origin. So in the last case, if I have double pair complex poles on imaginary axis, that is in the form of s by s square plus omega square whole square. So if I have repeated poles on repeated complex pair of poles on imaginary axis. So in such case also, on applying inverse Laplace, as you can see, it has the function of sinusoidal in nature as well as of ramp function into t. So this also produce a sinusoidal oscillatory function, and this will go on increasing till infinity. So this also leads the system to instability. So from this we can conclude that if there are multiple poles on imaginary axis as well as at origin, the system will become unstable. So these were the significance of pole, location of poles and the time behavior from their location. So next topic is the necessary conditions of driving point function as well as the transfer function. So first let us see driving point function. So these are the conditions that must and should be met for defining a driving point function. So the first condition is all the coefficients of both numerator and denominator must be real and positive. The second condition is if the poles and zeros are an imaginary axis, they should be conjugate, that is existing in pairs. Then the third condition is the real part of all poles and zeros must be negative or 0. So if the real part is 0, then the pole or 0 will be simple. So here from this it is understood that it should not be positive. The real part of poles and zeros must not be positive. Then the fourth condition is there should not be any missing terms both in numerator as well as denominator between highest order and lowest orders. So the fifth condition is the degree of both numerator and denominator must differ by either 0 or 1. And the last sixth condition is the terms of lowest order in P of both numerator and denominator must differ at least by 1. So these are the 6 necessary conditions that should be met for defining a function to be a driving point function. So the necessary conditions for transfer function. So here the conditions are almost similar but a small change. So the first 3 conditions will be same. Coefficient of P of s and Q of s must be real and positive. The complex imaginary poles must be conjugate and the real part of the poles must be negative or 0. So coming to fourth condition, here there is a slight difference between this condition and the previous condition. Here when I consider Q of s, that is the denominator polynomial, there should not be any missing terms between highest and lower order terms in denominator polynomial. But in numerator polynomial, we can have some missing terms or negative terms, but that is not allowed for denominator polynomial. So for transfer function, numerator can have missing terms and negative terms, and denominator must not have any missing terms. So, and the last condition is nothing but the degree of numerator can be small or 0 and independent of the degree of the denominator polynomial. So these are the conditions, necessary conditions of both driving point function as well as transfer function. So let us see some tutorials on pole zeros. So first the example is, so given a network function is n of s, which is s plus 1 into s plus 3 into s plus 4 by s square plus 2s plus 2. So he has asked us to find poles and zeros and plot them. You know, poles are nothing but values of s for which denominator becomes 0. Zeros are the values of s for which numerator becomes 0. So in this case, you can say the zeros are nothing but minus 1, minus 3 and minus 4. The poles are nothing but, if I find the roots of this denominator polynomial, it is nothing but minus 1 plus or minus j. So if I want to plot this zeros, I can represent it by 0. So one I have minus 1, minus 3 and minus 4. And poles I have at minus 1 plus or minus j. So minus 1 plus j, we have one pole. Minus 1 minus j, I have one pole. So this is how we plot the poles and zeros in S-plane. The second example, so here also we have to plot the pole 0 plot of transform impedance of the given network. So first let us find what is the transform impedance of this function. First, right, transforming this into Laplace domain, it is, as you can see, 1 Henry is nothing but represented by S. So that becomes 5 plus S. This is capacitor is represented by 1 by S. So this is 1 in parallel with 1 by S, that becomes 1 by S plus 1. Since these two are in series, so on applying KVL, this becomes 5 plus S into I1 I of S plus 1 by S plus 1 into I of S is equal to V of S. So on simplification, if I find the ratio of V of S by I of S, which will give me transform impedance function. So on simplification, I get this expression. So from this expression, I can get, so if I find the roots of the numerator, it will give me this expression. So from this, poles are located at -1 and zeros are located at -1.26 and -4.73. So the last example, so here he has asked us to find the driving point admittance, and from that we have to plot pole 0 diagram. So first let us find the driving point admittance. Since all are in parallel, this becomes S, this becomes 1 by S. So Z1 is 2 plus S, obviously Y1 becomes 1 by 2 plus S. Z2 is 1 by S, so Y2 becomes S. So Z3 is 1, similarly Y3 will also be 1. So next, since all are in parallel, I can add Y1 plus Y2 plus Y3 in order to get Y of S. So remember, I can do this only when all the branches are in parallel. If they are not in parallel, we cannot add the admittances. So on simplification, I'll get Y of S to be S square plus 3S plus 3 by S plus 2. So in order to draw pole 0 plot, I have to find the roots of the numerator. So on finding the roots, I'll get -1.5 plus or minus j 0.85. So it is equal to -2, I have a pole. In zeros, I have it -1.5 plus or minus j 0.85. So this is the pole 0 diagram for this function. So this concludes the concept of poles and zeros, their significance, pole 0 plot, and the tutorials on these concepts. So in next lecture, we shall see what is positive real function and solve some tutorials on those concepts. Thank you.